Hello, everyone. Can you hear me?
Yes.
Yeah. All right, great. Thank you. All right, perfect. Thank you. Yeah, so we are on Zoom. Give me a second because I haven't done this all the time. So everyone should be in, and we are recording, so I will be posting this video. If you guys see anyone that comes in, just let me know so we can let them in. Uh, but yeah, so video's recording, and I'm sharing the screen. So that's good. Okay. Yeah, so today we have a snow day, so we're doing this via Zoom. So I'm sure you guys realize we can't have the exam because the exam has to be in the classroom. So I'm going to postpone the exam to next week. All right, and instead today I was only going to do the exam one half of today, so that what I'm doing is I'm just moving the lecture up from next week to today. So today on the agenda then, and I guess before I get started, are there any questions? Okay, no questions. All right, great. Yeah, so the exam is going to be next week. Today we're just going to do lecture. So on the agenda, let's go to the table of contents. And you can see, and I think someone has their microphone on. If you can mute your microphones, really appreciate that. Okay, so he's got their microphone. I think that was addressed. Yeah, so today on the agenda, let's go to Brightspace then. As you can see, we've covered your first neural networks. You have a homework assignment that's due. And I saw some of you have started to submit that. We've got cross entropy, which we've covered fully. So today we're going to get into neural input optimization. The goal would be to finish this topic. So we'll finish this today. So I'll do a quick review and then we'll get into it. And then I have in the second half of today, we'll get into these PowerPoints over here or PDFs, which are about loss functions. So we'll talk about loss functions. So we'll do a 1 hour and 20 minutes from 5 to 6:20, take a 10-minute break, and then from 6:30 to 7:50, we will do this section. So that I think works out well. And then that takes us almost to the end of some of these theoretical ideas, and we'll start CNNs probably next week, or actually, because you guys are having the exam next week, the week after that. So we get into the image processing and the third of the semester. All right, so let's take a look at this. So this is neural input optimization, the topic in question. Let me close this. All right. So as you know, this is what you guys are working on for your term project. I'm going to click on NIO. It should take us to the repo. Today we're going to, as you know, neural input optimization in its simplest form is about optimizing the input. We freeze the weights of a trained model and we backpropagate data from a loss function to the input itself. So we've discussed that and we'll continue with that today. So you can see here, this is all the text that we provided. Today we'll get into all the details of an actual problem. Now, I did say that the code is going to live here where it says Civis. And then you need to go to runs. And if you remember, you had runs 1 through 4. I've added a new run 5. Guys, if you can mute your microphone, please. I've added a new run 5. It's very similar to run 4. This one is it's got more information for the lecture today. So this is the one that I'll be using because it's got more examples that I want to try out to discuss the issues. So, and then it uses the same PDF utils.py file. We discussed in the last video how to load this, and you guys know how to access the data set. Remember that the data set I'm using is proprietary, so I can't share that one, but I was able to create this one, and you should be able to at least do some of the running and look at the video just to make sure the code runs, and then you will, of course, get a new data set for your term project anyway. All right, so I'm going to click on run 5. And I'll just quickly go through the basic idea. So remember, we've got our libraries. We've covered this in the previous lecture. We load the data set. We can print out the columns with ID numbers so that we know which variables to select. So obviously for your term project, you need to really try to understand what it is that you're trying to solve. This is how we can do the correlation matrix. So this is helpful. It's very helpful. Let me just get a light here. See better. Kind of in my basement, so it's not great. All right. Yeah, so we do the correlation matrix. Then this is very important. This is where you select your inputs and your outputs. So these integers have to map to these values over here, which is what you are essentially selecting. Okay? Then we load the data, we do all the steps, I print the shapes, do the random split. As you can see in my example, there's 4,000 training samples and 1,000 test samples. This is very important. I have vectors of 7 for the input and vectors of 3 for the output. And remember that this is a regression type of problem, okay? So that's a really important point. Remember that I'm using PDF utils, which essentially is it's everything that we did before with regression and classification. I just created this class this object-oriented class so that I could simplify some of the steps. Remember, we now normalize or standardize both the inputs and the outputs in a regression problem. So keep that in mind as you're working on your own problem. Create the data loaders. And then I have 2 architectures. I still only have 2 here. There is a third one that is the F1 plus F2 that we tried in the previous regression problems. I encourage you to try those as well, okay? Sorry, I'm letting some people in. So I encourage you to try that one as well. The F1 plus F2, having a really good model, a really good train model, what we call the forward model from step 1 is really important. So this is simple net, residual net. We've already talked about these. We instantiate the model, give it the means and deviations, create the optimizer. Notice that we optimize the parameters of the model. Learning rate is 0.001, and we're using an MSE loss. For most of these problems, even in step 2, we're going to be using a type of MSE loss. We're just going to hard code it as, y minus y hat squared instead of using the built-in function, although you could use this one as well. But it's really just to show that you can. And what we're going to do is we're going to use it multiple times, but just modify it a little bit, depending on what we're trying to do. And then finally, we have our model. We set it to train mode, and we do the training. Remember, the model returns scaled and descaled predictions. We train it, the pred scale with the YB, which also needs to be scaled, but that should be handled by the utility file. And then we train. So we train the model, and that's essentially what it is. Then we print I print some metrics of means and standard deviations, etc. So that's step one, and that's what we covered in the video or the lecture last week. I wanted to just do a quick recap of that. That's already covered in that video in a lot of detail. We spent a whole hour and 20 minutes or so on it. And that's step one. Now we're going to dive into step two. The actual, once we have a forward model, what are the steps to do neural input optimization? Okay. So I have my Colab. As you can see, I already set it up and I already ran Colab to do the training. So you can see it already finished training. I've got the little green check mark. So this is where I'm at in this, and it's ready to start on step number two. So before I get into like the whole algorithm, what I decided to do in this lecture is I've broken out all the functions or many of the functions that we will be using into smaller little parts so that we can try to give it some data and just see what's going on. All right. And so I'll kind of like illustrate, okay, there's this function. We're going to be using it later. This is what goes in. And the goal of this will be this. Now, keep in mind, this is actually the hard part of your term project. Your term project should, in essence, give you the freedom to play with these things, to do actual research, and try to figure out, okay, what are the what do I do to get this to work better? Okay, so that's essentially the idea. Okay, guys, if you can mute your microphones, please. All right, so let's go ahead and let's get started with step two, NIO. So some of the utility functions. So I'll start with Z. Okay, so we'll play around with this concept a little bit of Z. Remember, C is the actual thing that we're training to produce X's, which go into the model to produce outputs, Y's. Okay? So here we have, let's just like do this. Let's do that. All right, so the first thing we do is we create and actually I'm going to move this down. We create some kind of a random vector, just this one, like that. Notice we're going to call it CInit. It's not even the final C. It's just an initialization of C. Okay. And notice I'm just using torch ran 1, 7. So we can do print. And this is, the code is not a lot, but some of it might be a little bit tricky to understand. And so we really want to take our time with this, I think. Okay, so CInit shape, and then we can just print CInit and see what happens. Okay, so let's run this one, and you can see, so it's 1, 7. Remember that NIO has the ability to do batches. So that's what, I gave you the example that we could generate, let's say CInit is password, so we could generate 2048 passwords in one batch. But in this example, I'm trying to keep it as simple as possible. So I just have 1, 7. The vector 7 is because it's of size 1. Okay. So we print the shape and then notice that the values are random. So we got a 0.22, a 0.23, a 0.29, 0.33, 0.98, 0.62, 0.26. Just some random numbers. However, we want to like change these values to be somewhere in the middle of a sigmoid range. And this is just an example of how this might be important, right? The initialization of this vector, may require that the distribution be, a normal distribution or a special type of distribution. This one just tries for it to be middle of the sigmoid range. So let's see what that kind of does. So notice here first, I'm going to take, so we can imagine that if we generate another random z, it's going to look kind of like this, but just shift it a little bit. But notice that they're all like 0.22, 0.98, something like that. This one will take 0.4 and multiply it times all of these. Okay, so we're just going to do that. And you can see that the values now 33, 23, 0.11, 0.20, 0.18, they're a little bit more closer to something like this, right? So they're now a percentage of that 0.40. Okay, so we've kind of like scaled them a little. Okay, and then I may also want to have a fixed part, not a random. So the only the first part was random, right? This 0.3 just makes them more, we're going to shift them a little bit more. So now if I repeat that, notice they're now more like 0.35, 0.41, 0.50, 0.49, 0.57, 0.61, 0.64. So as you can see, they're the middle of the sigmoid range. So the sigmoid function gives you values between 0 and 1. And this produced now values kind of centered around 0.5, but with some randomness. Do you see that? So that's essentially all that I'm doing. So this is something worth exploring, or you can start out with this as you try your example, but it's just a type of initialization of the vector. And this is something that I encourage you guys to do research on. Okay? So now that C in it is done, excuse me, we're going to, and feel free to ask questions if you have them, do something else. So I'm going to run it through a logit. So let's do torch logit, cinit. You can see now that it has just taken them and made the values to be in some kind of a scale between like negative 0.5, and negative 0.78, right? So it's just another function that I'm applying. And now it almost seems like they're standardized in a way, right? So it's almost like that standardization that I've been doing all semester. They're kind of zero mean, maybe. You could argue that, right? So it's consistent somewhat with what we've done all semester of normalizing our data. So these steps are things that I encourage you guys to play with, given that the the whole point of this is going to be to train this C vector, right? So its initialization, let's say you initialize that vector with all ones, for some reason, like all of these were ones. That may not converge to the answer, right? And so having a proper initialization or something may actually be something worth looking at. Okay, now that I've done the torch logit cinit, then notice that all I'm going to do is take this tensor and I'm going to run it through this function, torch nn parameter. And that is what finally creates z. And if you notice, this one is actually quite straightforward. If I click on this, what does it do? It essentially takes that same vector, right? But now it creates it into a torch tensor, and more importantly, it sets the parameter requires grad as true. So it made it into a parameter in a neural net, and the requires grad equal to true. If you remember from the NIO GitHub repo, I said to you guys that the key thing was to set this to requires grad, right? So the input over here should be requires grad. We also freeze the weights of the model. So the model weights are frozen, but we set this to requires grad so that when we do the optimization, this is the parameter that gets optimized. Any questions on that, guys? So that kind of completes a very important part of what we're doing. Yeah. So initialization in all machine learning models is essential. The thing is, usually when you guys build a neural network, because it's geared towards training the model and everything, it handles that internally for you. But here, you are actually freezing the weights of the model, and your goal is to optimize the input. And so we got to play a little bit with that to help the model out. All right. Now that that's complete, like I said, I'm not really even following a logic here of the algorithm because I'm just showing you like independently various parts of it before we start to put it together. Okay, so now I'm going to go back to that Jupyter. Remember, I'm updating these. So I'm currently on run 5, which is, the one that I would recommend you use. It's got more intuitive, up-to-date parts. Okay. So we've done that. So we did the C init. Okay. Now we're going to do this function called regularize the C vector. And essentially here, it's just a type of an MSE. Okay. So this is just a type of MSE. It's just a type of the mean squared error function that we've used for regression training. So essentially what we do is here you square every value in the vector and then you sum. So it's essentially like MSE. And why do we do this? Well, this is something that in the loss function we can do later. It's a useful way of looking at the whole vector. Remember that we're trying to optimize the C vector. So as we're training, we're gonna want to look at this vector and just calculate like one single metric about it. And this is a good one. So this is a useful way to get a metric for the vector that we may want to minimize or maximize later on in the loss optimization. So this is that joke I told you guys that when you take MSE, the loss function equal MSE plus this and regularize, you got a Ph.D, right? So that's essentially what this is. So you have define regularize Z. Notice it takes the C parameter, right, which is our C input here of size 1,7. And notice that all we do is we take all the values in Z and square them. And then we take torch sum and add them. So we can essentially copy this one and break it up and take a look at its behavior. So here I'm going to maybe put it here. Okay, so we're going to imagine Z that we already have, right? We have our Z value. So we can just take a look at it. We square it and notice that all the values are now positive, right? So we just squared it essentially. Then we take the sum of it, and that should give us just some number. As you can see, the number is 1.35, and then we're going to multiply it times some strength, which is this value, a very tiny number. So now I'm just going to run regularize with the C vector. Just like that. I need to add this one. So add the regularized function, and you can see now it just it made it much smaller because you're multiplying times a tiny number, 0.0014. So what that does is, as we're going to be training, we're going to have loss equal MSE something plus this term. And so eventually, as you're training, the value is going to be 1.35 multiplied times 0.001. to give you 0.0014. And this value, as training goes on, will change. Okay, so this is a value that you can now control in your loss function. You know, do you want to minimize it? Do you want to maximize it? And so that is something that you will be able to use for the training. Do you guys understand? Does that make sense? Questions about that? Okay, no questions, it seems. All right. Yeah, so that's the idea. Okay, so yeah, that's the regularized parameter. It's something that we'll see in a little bit as we start putting everything together. But when you see everything together, it may not make sense. The next thing that we're going to use is we're going to get our actual x from the C lambda function. So if you notice, the C value that we generate that the model is training. So what is the parameter that's being trained by the model? Well, it's this one, the one that requires grad. But if you look at this number, it is actually, 0.65, 0.13. So it's actually, like standardized numbers, right? Zero means standardized numbers. It has no relation to our X input. Our X input is what? Our X input is, natural gas, production, or coal flow or coke rate, things like that. So these are values that could be 2,500, 90, 10,000. So these are different ranges, but this is not that, right? Another thing that you must remember is if we go back to our function, our model, right? Residual net. Remember that net receives X unstandardized and then it standardizes it inside. So therefore, the X input that we must create from the C vector that we're training has to be unstandardized. And so that's something that we're going to accomplish with our lambda function. So I'm going to go over here. And now we're going to add this lambda function over here. So essentially, get x from C. This is a lambda function. It's just a standard Python construct for building functions like in one line. So here we ensure that the x generated from the C is within the clamps. So remember that not only is it in the appropriate scale, in the real scale, but also it's got to be clamped. Clamp means, if you remember, because we're doing something that is physical, a process, right? That's chemistry, physics, etc. We want to ensure that, we're not saying that the temperature is going to be 5 million Kelvin, right? So that's probably, I assume that's really hot, right? So that wouldn't exist, hopefully. That's not a non-physical temperature, but even, much smaller temperatures would not be physical in the context of your problem, right? So that this clamp is going to depend on your research as well of the type of problem that you're doing. So here, for instance, what I'm going to do is I'm going to have the function, okay? And then I'm going to have the clamps. If you notice, the way that this function works is, it's called get x from z. So it's when you call it as a function, and within the parameters, you're going to pass the C tensor. Then it's going to grab clamp min. So there's a clamp min and a clamp max. So for instance, for one range, natural gas should be between 0 and let's say 200. And coke rate should be between 0 and 1,000 for whatever reason, right? So clamp min is a vector of 7 and clamp max is a vector of 7 that will have the minimum and maximum values for that range. So here you can see that we're going to predict this C value, we're going to start with clamp min, let's say 0, plus, and then here we're going to say clamp max minus clamp min. So clamp max might be 200 minus clamp min 0, so 200, Okay, so we start at 0 and we can add up to 200. That's essentially how we're going to modify the values. And obviously, these are just the ranges. We're going to determine what, how much we're adding, right? So we're going to, within that buffer, so that quantity between the minimum and the maximum, right? The way that we're going to figure it out is by multiplying it times z, the c value. So for every one of the 7 values, we're going to, let's say one is, 0.5. Okay, if that's 0.5, then it's 0. 200 times 0.5 is 100. So therefore, this value is 100. Okay. Now the sigmoid here is, once again, remember that you're training the model to produce good values. So that C is changing a lot. But whenever we run anything through a sigmoid function, it should turn the values into oops, I didn't mean to do that. It should turn the values into values between 0 and 1. So if I do print Z here, and then I do print of sigmoid C, torch.sigmoid C. Let's see what happens. You can see that 1 is minus, pluses. Here, all the values are between 0 and 1. Okay? So that allows you then to take, let's take another example. The min is 50. And the clamp max is 250. Okay? So then it starts at 50. You take 250 minus 50 is 200. This value comes out to 0.25. So 200 times 0.25 is 50 plus 50. That should be 100, right? So that should be the correct math. Please correct me if I'm wrong, but hopefully that should make sense. So we can do that example actually. Let's say the min is 50. Min is 50. The max is equal to 250. So then the difference is 250 minus 50, which is 200. If torch sigmoid of C for one of the 7 values comes out to 0.25, then we multiply that times 200. That's a quarter of 200, which is 50. So therefore, the value is going to be 50 plus 50. Oh, that's 30. 50, which is equal to 100. And that's essentially the value that is predicted for that one of 7 values in X. So now if you notice, X comes out as being in the correct range of our example. So now let's run this one. I'll comment these out in case we need to come back to them, but I don't want to delete them. Okay, so let's load the function. So that function has been loaded. So now let's create some clamps, min and max. So I got my clamp min and max, which is what I was saying, right? And now I'm going to run it through the function to create a value called xguess. I'm calling it temp, so there's no confusion between the values that I'll be using in the code a little bit later. All right, so it's going to take z. Notice get x from z. We call it get x from c. In parentheses, we provide the c vector, and it's going to do this logic with clamp man, clamp mix, clamp min, clamp max. And here we go. So you can see now the values like 93, 73, 27, 1,420, 210. If you notice, all these values are within range, right? So 0, 93 is between 0 and 200, 73 is between 0 and 200, 27 is between 21 and 32, 1,420 is between 1,300 and 1,500, 210 is between 150 and 250. The problem with this, of course, is that these are random values currently. But remember, this is actually the goal of what you're doing, right? So what you're doing is you're trying to generate this input that generates the output that you want, your desired output. Okay? So yeah, so that's kind of it works, like the machinery works. The problem is the values right now are coming out random. What you really want is for these values to come out like the correct ones. And that's where the training is going to do the magic and all the heavy lifting for us. All right, guys, does this make sense? Are there any questions on this idea? This is really important that you understand. Okay, I'm not hearing any questions. I'm assuming you guys can see and hear everything. All right, the next thing we're going to look at is something called the soft penalty box for loss. This is really important. This is a standard optimization. I didn't invent this. This was, it's been around in textbooks and everywhere. The soft penalty box for loss is as follows. So let's think of this example. You guys do a regression. You know it very well. And essentially, what do? You want pred and pred real, or real, sorry, real, right? You want to minimize these values for perfection. Like you want the predicted value to be exactly as the real value. We did this actually in the baby NIO example. If you remember, the loss function was this one, right? Y pred minus Y target power square mean, and that was the loss. We use this loss for when we want the target value to be the same as the real value. Or we want the predicted value to be the same as the target value, right? We want equality. And that's usually what you do in regression. But in this type of problem, you have several different cases. Maybe what you want is, equality. So this is equality. Equality. But what if you want pred not to be equal, just to be greater than real? Do you see that? That's a different type of relationship. So let's call it greater than. Greater than. And the loss function needs to be tweaked. However, that's straightforward to do. As you will see, it's actually very clever and an elegant solution. Notice that all of these are still all going to be based on MSE. So we're always going to be using MSE as the underlying, and then we're just going to tweak it a little bit. And when I say MSE, remember, it is this function, Y pred minus Y target squared, and then the mean of it, right? So that's essentially, so all of them are that. But now we have real different cases. For instance, let's say I want, and this is in relate, by the way, also, this loss box that we're going to be using, let me go back to the code. So this soft penalty box for loss that we're going to be using is for the outputs, okay? Or for the inputs, right? So it just depends on what you're trying to do. But we need to specify for which one we want to use it in the optimization. So the next scenario is, what if you have two reals? You have a pred, and you want the pred not to be equal, right? So here I should probably rewrite this as equal. We don't want it to be equal. We don't want it to be greater than or less than. Instead, what we want is we want something like this. Real one greater than pred greater than real 2. So do you see here, we want the value to be in an interval, within an interval. We want this to be within an interval. Okay, so we want it to be within an interval. To accomplish this, we're still going to use MSE, but we're just going to play with MSE a little bit, because now we're going to have these values like an upper and a lower bounds, and we want to make sure. So if you notice, it's like taking this one but extending it to have two cases in the loss function. And so this is the problem, that you're going to encounter. When you do MSE, you always do this, like your regular regression, your homework. But for NIO, now you have this or this. Keep in mind, this one is actually just a special case of this one. So you can generalize your code to just use this one. I just kind of did my code to illustrate this a little bit more, to just, for teaching purposes. But you guys obviously can make your code much smoother. Any questions, guys, on this idea? Okay, I'm not hearing any questions. All right, so I'm going to comment this one out, because that's just like the theory. And now we're going to take a look here at. So here's the function. This is, as I said, the soft penalty box loss. So let's take a look. Control. Okay. So notice this one, I'm going to do this with the input. So it's going to take X. Here's the lower and the upper, as I just explained. And then there's some kind of a strength that you can use for this one, just to see how, what contribution this will have to the overall loss. Remember, we're doing MSE plus something. So we want to have little metrics to control the impact of these variables. So if we look over here, this is very interesting. We have in parentheses like that and like that, right? So we've got two terms, this one plus this one, okay? We have those. Both of those just go into this, produce a number, and then we multiply it times the strength. So let me actually load this function so I don't damage it. But let's ignore the strength in parentheses, because that's just multiplying that value to make it kind of tinier or actually higher, right? So it could be one or the other. So now we have this, okay? And we're going to be using clamp min and max for these values. So very interesting. Let me move it down here. So we're going to use this one. So X guess temp, we had already calculated that value, right? X guess temp, we had this value over here. So let me add a few cells here so we can print X guess temp again. Okay, so there's, oh, sorry, I just X guess temp. Okay, so X guess temp, as you can see, I've got some values there. Okay, then we can basically separate this out into two parts, given that we're just adding them, just to simplify this a little bit more, right? And we leave this part here. So now we can take out this parentheses. Well, actually, no, let's leave that parenthesis in. Okay, but really, what do we do? It's a vector, right? So the vector is going to every value is going to be squared. As you can see here, the values get squared, and then all values are summed. So actually, you know the behavior of that, so we can ignore that, right? And just focus on this specific part here. So if you look, now I've got lower and I've got X, and this order matters. So I'm going to do lower minus X. Remember that lower is actually clamp min. Okay, so we can replace that lower with clamp min. Both of these should be vectors of size 7. Okay, so if we do the difference, and actually let's print clamp min as well. Print clamp min, there we are. So we've got our X guess and our clamp min. And now we take the difference of the two. Okay, we run that. Oh yeah, should be X guess temp. And there we are. So it takes the difference. Do you see? Here, we're focusing on the clamp min and X. So remember, this is called the soft penalty box. And we're essentially trying to optimize so that the value pred is somewhere between real 1 and real 2. So 1 is the min, 1 is the max. So we're currently comparing pred to the min, and then we compare pred to the max. So here we took the difference of it, clamp min, clamp, and X guessed. And so it gives us the difference, right, of what it is. But there's a very clever trick here. Let me add a couple of cells. Notice that after that, you run this. So let's do res, and I print res. Okay. Now I run res through this relu function. I run res through that relu. And guess what happens? Relu did not let any of those values through because Relu only allows what? 0 and positive, right? It's the hockey stick. And so notice all the negatives became 0, the zeros stayed at 0. So this trick of taking the difference and running it through Relu is how we can control so that essentially what it does is it returns like it failed. It's a 0 loss. Right? So let's see. So here the value 93. 0, 73, 27. Yeah, actually, I take that back. So what happened here is it returns. I could see that the zeros is what we want, right? So we want the loss to be 0. So it's returning exactly what we need, which is that it looked at these values here in this vector, compared them to the clamp min, and it realized that they were all above clamp min. And because they're all above clamp min, the ReLU returns 0 for a loss. So we can test that by trying a different clamp min. So let me grab where we created clamp min somewhere. If you guys see it, let me know. Here, okay, clamp min. So let's grab clamp min. Here, probably. Okay. I'm going to say, okay, so the values are 93. I'm going to make that second value 200. You guys see that? So I want, this is the min of that. So I'm setting it to 200. So that should pop up, I think. So if we try it, there it is. I made that 200. Then I run this difference. That has changed. And now, there it is. Perfect. Beautiful. How pretty is that? Look at that. Everything was 0, which was great because the vector was all above the min. But now that I intentionally made this 200, which I know for a fact that's greater than 93, guess what happened? The value here in the difference becomes 106. And when it runs through the ReLU, it stays at 106. It doesn't get converted to 0. So therefore, this is a loss. So like you guys, you know how when you're training, right, your loss is 50, 40, 35, 31, 28. So you want it to go down, right? But if you have a situation where the value is above or below this min, then your value was 20, 25, 17, 7, 106. So it jumped back up to 106, and you don't want that loss. Do you guys see that? How elegant is that? Any questions? Does that make sense? Can you guys hear me? This was really important.
Yes.
Okay, perfect. All right, yeah. So this one is really important, okay, that you should understand because it's actually an NIO when you're dealing with a lot of regression kinds of things. This is a very important metric that people are going to want because, like I said, this one covers all cases actually, not just greater than or less than, but if you use this one, it covers really well. Okay. All right, so perfect. And the opposite then applies to the clamp max. Just notice that it's the exact same logic. So we did this one, clamp min. Clamp max is the same as x, but inverted, right? So now instead of lower minus x, it's going to be x minus upper. So the upper end, and then it runs through the ReLU, and it's going to be the same effect. So, and then those two are added. So effectively, that's the loss function that you can use whenever you want to optimize something to be within an interval such as this one. Okay? All right. So let's remove this one here. Let's now just run it in full to see the effect. What's that? 2. Just going to run this short. So I'm just going to now create the function. There it is. So we run the function because we're going to need that function later. So I'm just trying to make sure I don't modify anything unintentionally. Then you do the soft penalty. And then, as I said, you give it X guess, clamp min, clamp max, some kind of strength. Notice the strength there is 10. And you run it, and there's your loss. So it starts to give you some kind of a loss value that you can use. You can scale this if you'd like, but it's a loss parameter. So when you were doing loss equal MSE function, now plus regularization, plus softbox penalty, and so on. Okay? So that you can optimize your different metrics. All right, guys. So I think that is like an overall breaking all the different functions, okay, just so that things were a little bit more clear. Now we're going to get actually into the algorithm. So we're going to get into it. Oh, my battery's always running out. But yeah, from this point on, I'm going to get into the algorithm. So I'm just going to grab this code. And now this is step 2 of NIO after training the forward model. Step 2 of NIO after training the forward model in step 1, which is essentially your normal, any kind of regression training that you're going to do, multiple input, multiple output. All right, so let's add here the code, and now we're going to run it just in parts, but it's exactly what I've said already. Notice I got my torch 1,7, do the 0.4 plus 0.3, make it into the parameter C. You can see C is now requires grad is set to true. So it's going to be the parameter. Oh, yes. Then the next step, if you remember, was going to be to create the optimizer called optimizer infer. But notice that we use torch.optim.atom, but the parameter is now Z itself and not the weight, the usual model.parameters. And then the learning rate here is 0.03. You can play with that. Try to figure out. Later on, we're going to see we can also use a scheduler, which might be a little bit better, which actually is here. So I keep doing this here. So now we grab the scheduler. So what is the scheduler? It's a very simple strategy to have a learning rate that is variable. So you might want to have a variable learning rate when you're doing your training. Okay. This is, sometimes it's going to be 0.03, then maybe it becomes 0.003, then maybe 0.0005, and it's adjusting itself depending on the needs. So the way to do that is we instantiate a variable called scheduler using torch.optim.lrscheduler.steplr. We tie our optimizer to it, and then we just give it some default parameters, and that's it. We build that scheduler, and then throughout the code, whenever we take a step back propagation, we're going to adjust the learning rate via this scheduler. Okay, and then once we've completed that, we just can print the shape of Z and check that it requires grad. So it's 1,7, and it does indeed require grad. Okay, any questions? All right, so now the input, the Z input is complete. Now we proceed to look at other things. We've already instantiated the lambda function and discussed it, how we're going to use it. We're going to give Z to that lambda function and we'll return X. Now let's talk about the output. So in this example, remember I have three variables, FT8, HMT, and TGT, and I want all of them to be greater than certain values. So I need FTA to be greater than 1900K. I need HMT to be greater than 1700K, and I need TGT to be greater than 100 Celsius, okay? Or 100 C. So these values is something that you need to figure out, right? So you need to figure out what these values are going to be. So here we're going to think about that. So let me grab and I think I actually changed them a little. So you can see there are actually 1800 and 2600. So these are changed. But that was just an example. As I've been playing with this, yeah, I did change it. So here, notice, so you essentially say target output, not scale. So this is going to be like a minimum, if you want to think of it that way. 70, 1800, 2600. And then you have a margin out that you can give it to kind of indicate, okay, I just need it to be greater than 70. So, well, the ceiling can be 1E6, where 1E6 is 1 million. So from 70 to 1 million. For 1800, same. So from 1800 to 1e6, so 1 million. But for the 2600, you really do not want it to be a million, obviously. So instead, you want it to be just 200 from 2600 to 2600 plus 200, which is 2800. So this is another way of creating like something similar to the clamp min and max, but for the output. So we can see that here now to create them. So notice, so inputs and outputs essentially have these clamps. I just used the word clamp for inputs, and I'm using bounds for outputs. So notice here I create this lower bounds glub, which is just this one over here, target output, not scale. I clone it so that they're not linked together. And then to create upper bound glub, I just take target output, not scale, plus this margin, essentially. So now if I run these, you can see that the minimums go from 70, 1800, and 2600 to 1,070,000, 1,018,000, and 2,800 because the margin here is 200. So I'm just showing you different ways that you can do this. This worked. But yeah. So these are ways to create these examples. Any questions? All right. The next step is, of course, we cannot just use the values as they are because they are in different scales, 70 to 2600. So we standardize them. Luckily for us, the utility function already calculates these values, y means and y deviations. Remember, if it's inputs, it's x. If it's outputs, it's y's. So then you just take the exact same approach we've been taking all semester, standardize lower bounds, upper bounds, and even the target output not scale that we had originally, you can scale it and use it as a parameter. So there you are. So all this is doing is standardizing those values. All right. So that is essentially that. Now comes, I think, the last part before we start getting into the loss function. So I'm going to take, this is just as the title here implies just some parameters that I have available. Okay. So the first parameter, all right, so the first parameter is called the mask. You guys use masks in GPTs, but this is way simpler than those masks. This is essentially just the following. This constraint mask refers to the output vector, okay? You know that the output vector has three values, A, B, and C, right? You guys know this. So that's the three variables here. Well, let's just go back here. So the three variables, these three variables, right? So, or these, greater than 1900, greater than 7. So these raceway, hot metal temp, top gas, something like that. Okay. So that's what the output looks like. So then this output will need to have a mask that indicates how you wish to optimize each of these values. Okay. So for instance, my mask here will take values 1, which I believe it's equality, 2, which should be like greater than, none of these symbols. Wait, hold on. Yeah, so equality greater than, for instance, and 3 should be within range. Okay, so whenever you're optimizing, what's nice about this is you might say, okay, I want the first variable to be actually equal to the target. Or you say, and so in that case, this is a 1. You see that? But then you decide, no, I want the first variable to be greater than, so then it's going to be a 2. No, I want the first variable to be within range, so then it's going to be a 3. Do you guys see that? So that's essentially what you're doing with that. So you're controlling um, each of these, you're controlling each of these variables and how you want to optimize it. So there's going to be a loss function, which is what we're going to look at next. And the loss function takes in this mask, okay? And essentially, with this mask as an indicator, it selects which loss function to use. But it's the same thing you already know how to do that I just explained. Is it the softbox penalty? Is it just the ReLU individually? Or is it the equality? Y minus y hat squared. It's fairly straightforward. But yeah, there will be a constraint mask, and that's associated with the output. So you can see here, it is 2, 2, comma 3. Okay. Now the next step is another parameter is going to be this parameter alpha, which you will see later is just to control the strength of the main loss term. So we'll see that later. We're going to have loss equal alpha times MSE function plus maybe 1 minus alpha, things like that. So that allows us to control that. So that's alpha. Then we have this overshoot margin. And then we're going to see this is a parameter that it may be optional or you may need it. You may need to play with it as you're doing your research, but you control these values essentially. And it's basically something you add to the clamps or the lower and upper bounds just to give it a little bit more margin, so that maybe sometimes the model is too restrained because remember, every prediction is still going through the forward model. So the forward model just may not be able to produce inputs. So then this might constrain it a little bit. So we'll talk about this one later, but it's called an overshoot margin. And then finally, we've got these constraint weights. And this is just to indicate where you want more focus on the training. Do you want it on for instance, here, this would indicate that the second variable should become more important than the other two. And so so when do you use these parameters? You use these parameters as you're building your model. You're going to, hopefully you run your model and it works initially, but then you're going to realize, you know what, it's not able to produce things. So I'm going to have to tweak it a little bit, play with the values until it starts to produce what I'm looking for. Okay. So this is a way to give you flexibility. This is actually to help you out in the project. Later on, as time permits, I will show you that there is, in fact, a methodology to calculate these from the losses and adjust the weights automatically. So that's something, but for now, I don't want to overcomplicate things. So let's just keep it there. Okay, so these are parameters. Overshoot margin and constraint weights are parameters that you will need to play with. Okay. All right, so we did that. And what's great about this playing with all these parameters is really gonna give you some insight into how loss functions work, how models are trained, and all of that. All right, so now we've completed this part. So now let's let me see. Oh yeah, so I've done all of this. Look familiar. Done this, I completed this part. And now guess what? This is the loss function. And once we have the loss function, if you notice, the next step is really just to run the NIO loop, and that's it. Okay, so let's do but a lot of the things that will go into this loss function, thankfully, we've already discussed when we broke out the code. All right, so it's called constraint loss. All right, so we're going to focus on this one now. So in the past, if you remember, you guys, whenever you did loss in your code, you did loss, and then you did something like torch dot MSE, torch dot MSE. And that was it, right? That was absolutely it, and you were really happy. Now, in this approach, your loss is actually going to be this one, constraint loss, with all of its parameters that you're defining. Okay, so that's the difference. It's before or now, this constraint loss function. Comment here. All right, so let's analyze it. So it's actually not that difficult to understand because it's really several sections that are totally independent. So constraint loss takes in ypred. So what is ypred? The predicted vector, output vector of 3. Okay, guys? The predicted vector, output vector of 3. Remember, vectors of 7 go in, vectors of 3 come out. So ypred is the predicted vector. Y target is what you want. But you also have the upper bounds, lower bounds. You have the masks to indicate for each variable, is it equal, greater than, margin. You have the weights that allow you to play with the parameters. You have the overshoot margin that we talked about that you can try out. The overshoot margin is just used in one of the cases, right? So, and then you have some kind of regularization weight that you can modify. So you start with loss, very much like this loss was just dependent on this. Now your loss is going to be dependent on all the activities happening inside constraint loss. So that is why we have a loss here that starts at 0. But as we go through this for loop and all these if statements, etc., that loss is going to become, loss equal loss plus what we just did. And it's being updated in the logic. So let's take a look at initially the for loop here. Okay. So actually, guys, let's do something because this is going to take more than 6 minutes probably. It's 6:15 right now. How about we take a 10-minute break because we would take the break at 6:20. So let's take the break right now at 6:15 and let's come back at 6:25 and we will pick up here. Does that sound good?
Yes, sir.
Yes, sir. All right, great. So I will end this video and you guys can take a 10-minute break and then we'll come back and finish this second section.